Let's go to moon, to our backyard. All right, so we've looked at it. You can name the phases. You can even draw the phases, starting middle of the circle, connect the terminator, 3 ways. Right, so you know that. You even know, if you worked on that, it was pretty hard, the drawing to show around when each phase rises and each phase sets, different for each phase, right? And why that's happening, why as moon orbits Earth, the side facing sun is lit, but the side facing Earth will show phases. Okay, so what we're going to do here, pretty quick, since we've studied Earth, in many ways the most complex world, or at least more details, we're going to do moon, our backyard. So we'll review quick, and this is important to understand because it'll tell us so much the size or the width of moon. The distance, how far away is it? I mean, you look up, it's hard to tell, but it looks close. I don't know how close. We'll talk about, and the motions, quick review of that. That's going to be this video. Then we will talk about missions. I'll briefly mention, did we go? During what war? How many human attempts did we make, and how many of them succeeded? Was it one, none? Were the failures? Did we work? What happened there? Number 3 is the origin. And we'll see how this informed our understanding of this. We'll look at 3 ideas that people had pre-1987, and then exploring the evidence, the likely candidate for where moon came from. Then moon layers, interior, does it have a magnetosphere, does it have an atmosphere? You'll be able to figure that out. Understanding Earth, you can see what's there and what's missing here. And then we'll go quickly to moon's surface, features, past and present changing processes. We'll check those 4 that we discussed for Earth's surface changing. And then finally, highlands, the light area. If you put on sunglasses and look at moon, it'll really bring out the light and dark areas. If you use binoculars, and maybe binoculars with sunglasses, you'll really see the highlands and the Maria, dark areas. And you should know one feature by name. Ready to go to moon? So am I. Let's do this. We're going to talk about got this laid out here. We're going to talk about the size and the distances. Okay, cool. So moon, our backyard. What is up with that? Let's come right in there, shall we? Good. And this tells us so much, right? So if we think about moon and Earth, here's Earth. How big is moon? How big is moon? We kind of went through this, right? I mean, would it be the same size as Earth? Would it be, my fist, half as wide as Earth? We'll talk about all this. 1/3 as wide, 1/4, 1/5. Okay, how big is moon? We'll get to this again. Well, we talked about moon is 1/4 as wide this way, 1/4 as wide top to bottom, 1/4 as wide front to back, 1/4 as wide side to side. Shrink it 1/4 each way, and you get that. Earth, moon. That informs a lot. So you should be able to draw that. You can show your friend, right? Okay, if I draw Earth, then all you can look at just the width. And we're going to do this for all planets in chapter 7. So make sure you've got this. This is one diameter of Earth. The capital D stands for the width or the diameter from one side to the other, 1 DE. Now I could use the symbol for Earth, which is a circle with a plus sign. It's a "you are here" sign, basically. But DE, maybe that is easy to remember. Either way is fine. So if that's moon shrunk to divide Earth in half, and then divide that in half, that's 1/4 as wide. You can get 1, 2, 3, 4 moons across Earth. So that's the diameter, and one diameter that of moon is about 1/4 that. Okay. Don't draw an egg in here. You're going to be doing this, so don't go like that. It's a circle, right? On 2-dimensional, and 3-dimensionally, it's a sphere, not an egg. So I do see that sometimes. Draw it as a circle. We're talking about moon. You know, we're drawing a picture of what really is, right? Not perfect spheres, but close. Remember that the diameter of dot and circle stands for sun, and that may be written way too small. The diameter of sun is about 100 times the diameter of Earth, closer to 109. 100 is fine. And if Earth is 4 times the diameter of moon, then sun is 400 times the diameter of moon. That's important for understanding eclipses. Okay, so remember that. So we can conclude, remember it. How do you remember it? Just say it, throughout the day, look at it, remind yourself, say it to people randomly. They'll think you're strange, but that's okay. The diameter of moon, or the width of moon, is about 1/4 the diameter of Earth, which is about 1/400th the diameter of sun. Now, what does this tell you, though? So having studied Earth, this means more to you than just being able to block the sunlight during a solar eclipse. It says moon is small, so relatively, right? Moon is quite a bit smaller. And so what are the implications? We're going to explore this. Big. You could figure it out. You could guess. You're not always right when you guess, like maybe there's a missing piece, but here you're going to be right. Moon, when it formed, the solar system formed 4.6 billion years ago. It all formed. It was hot. It rubbed. There's radioactive material. It was hot when it formed, but it has cooled. That would be a good guess. Why? It's a small cup of coffee compared to a big pot of coffee. It's smaller. And because it's smaller, why? It's got less hot stuff. So it had less hot stuff to start with, because it's smaller. And it's got less radioactive stuff to start with, because it's smaller, right? And so we think it was hot, but it has cooled, and so it's not going to be active. Minor little subtleties we talked about, some warmth, not entirely cold, frozen, but definitely cool, not active. And that means that it didn't change its surface much. We'll talk about that. And so we'd expect an older cratered surface, showing its scars, whereas Earth didn't, because we changed so much. So small tells us a lot. Small tells us cooled inside because of these reasons. So not active, not as active, older surface. We'll get into that. Also, smaller, less mass. Less mass, less gravity, right? So that means everything has gravity, you and me too, but not much sticks to me, right? I don't have much mass. I don't have much gravity. Nothing obvious. So you and I, there's less surface gravity standing on moon, but you can stand on moon. This is going to be an important thing, and it's very close to exactly 1/6, as strong as Earth. Now, what's important to me is that means that if I'm in a room like this and I don't need a spacesuit, I can jump up 6 times higher with my leg strength. I can jump 6 times higher, and the only thing that matters is I can dunk a basketball. So, very cool. Of course, you shoot a basketball and it's like, went too high, too far, all kinds of crazy things. So playing basketball in a gym on the moon, I mean, that would just be so much fun. But it's got less gravity. You could jump higher if you didn't wear a spacesuit. We'll talk about that. So moon has a harder time holding gas to it. It has a harder time holding an atmosphere. Okay, that's a clue. This tells you a ton. It's cooled, and it's got less surface gravity. And by the way, a spacesuit with the pack that regulates your temperature and your air and all that, right, is about 180 pounds. And people are working on that and so on, but figure 180 pounds. It's like me jumping on your back, right? So on Earth, you step on a scale, and if it says 180 pounds, or you put that whole suit on with the pack and all, 180 pounds. But 1/6 of 180 pounds is 30 pounds on Moon. So you may not want to walk around with that. Imagine 180 pounds. You want to walk around with that. But 30 pounds, 15 pounds in each hand, man, that's doable. You might even be able to jump a little bit, right? A little bit. And you see that in your images of people walking on the Moon. Okay, we'll talk about that. Now, distance. Where are we over here? Let's take a look at the distance. Keep all those factors in mind. Let's talk about distance. So you know, average Sun to Earth distance, 1 AU, 93 million miles. A little closer, 1.5 million miles. January 4th, so January 1st you can tell people. July 4th, a little bit farther. But 1 AU, 93 million miles. This drawing is crazy, the size is wrong, you know that, but I'm just putting it down. So how far would Moon be? Well, Earth to Moon, you could put 30 Earths. 30 Earths. So my drawing is crazy. If you really wanted to draw it, you'd make a circle, then make a circle 1/4 as wide, and then you'd go 30 Earths out, and then you'd have a nice picture. You might enjoy doing that. 30 Earths wide, about, okay? That's like 240,000 miles, but I feel like that's getting to be too much information to memorize. You kept one. It's also 1/400th of an AU. We discussed this. 1/400th of an AU from Earth to Moon. Moon is Sun is 400 times farther away and 400 times wider, so it looks the same size from Earth. Okay, not exact, but close, all right? So how far would it be from Sun to Moon? Sun to Moon. Think of it this way. If you take a softball, if you take a softball, and you go 10 long steps, real long steps, away, put the softball over there, 10 long steps, and now I've got a grain of sand, size of Earth. 1/4 of that grain of sand would be Moon. Sun is quite a ways away, back of the big room. Earth is here. Moon is right next to us. It's right next to us. It's our backyard. And so, Sun to Moon is about 1 AU. I mean, it's like it's our backyard. Sunlight bounces off Moon and goes to Earth. In about 1.2 seconds, it takes the light to go that distance. Light's very fast, we'll get into that. So 1.2 seconds. What would it take for us to drive there? You go in the car, no speed limit, 100 miles an hour, maybe faster than that, but let's just say 100 miles an hour. About how long would it take? Well, you can do the calculation, you don't have to memorize this, but it'd take about 3 months. So imagine driving 100 miles an hour for 3 months without any stopping. Coasting 3 months. You know, you could do it. It's like, okay, probably be worth it if you could do it. What about by rocket? Well, by rocket, we don't go straight. You gotta kind of get into orbit and do some things. So it's not like a straight path. But by rocket, depending on if the technology changes, but as of now, about 3 days. And so that distance informs us this idea. Oh, wait, you can get to Moon in 3 days? And by the way, Moon is always right around you. So you're at Moon, you can come back in 3 days. You might as well stay there for overnight or have a picnic, go to the symphony, I don't know, do something, a concert. watch a game or something like that, and then come back. 1 week, spring break, extra credit, right? Wow. So by rocket, it's very doable. But you got to keep someone alive that long, so you figure you got to be able to keep someone alive around 7 days, a week, 2 weeks, something, whatever, depending on how long you want to stay up there. So the longer you stay, the more you've got, and you've got air to deal with, and water, and food, right? So talk about that. So moon is by far our closest astronomical neighbor. It is our backyard. We can go and come back. There's all kinds of great restaurants there, everything, but no, anyway. Remember those. And then finally, because this is going to tell us a lot about moon as a world. Emotions. Oh, by the way, let me do this. If you have a globe, this was 20 centimeter diameter, a foil ball, reduced 1/4 of that. Moon, Earth, here's Earth. How far would moon be? 1, 2, 3, 4, 5, 6, maybe 7 long steps away. Where would that look? In this room, I would go across the planetarium here to the pencil sharpener out there. It would be out here at this pencil sharpener, orbiting over here. Not that far, but also a challenge to achieve that mission, to be sure. All right, so one last thing to remind you of. Remember this, moon's motions. The time to orbit Earth is about, pause, come on, you gotta remember this. If you hear it passively, it just doesn't stick. You gotta figure stuff out, struggle with it a bit, then it'll stick. I'm going with 28 days, 4 weeks, nice and easy to remember, good enough. Does moon spin? You know, takes about the same time to spin as it does to orbit. This is called a what? Pause. Gotta remember this. Synchronous spin orbit. And some people sometimes just say synchronous orbit or synchronous spin, or synchronous spin and orbit. Why? Well, it's from the tidal effect. But first, let's ask this. If it's spinning, you know Earth spins, but Earth's spin is tilted. And you know what that does? Well, is moon tilted? Not much. We'll just say, basically no. What does that mean? Do you have seasons? Moon, no seasons. That's kind of lousy. Why does that happen? Tidal effect, remember, Earth pulls stronger on Moon's near side than the far side. Took a while. So that told us, what about a dark side, a side that always stays dark? Was there a side that always stays dark? If you put a light bulb out and you make a ball, or you walk around some object and always face it, you're going to see the light bulb's over there, right? The light bulb's over there, my face will get the light. If I turn around and always face it, then when I'm over here, my face won't get the light. There's no side that's always dark, so no. There is no dark side of the moon, sorry. But is there a near side? Yes, there's a side that always faces us. And that side goes through phases. So yes, there's a near side, a closer side, and yes, there is a far mysterious side that we can't see from Earth. It happens to be boring, like the back of a head. More interesting side is facing us. We will talk about that. Time to orbit Sun. Think about it. What are we talking about? It'll dawn on you. I'm just going to leave that. softball, 10 long, long steps out there. Earth, grain of sand, moon right there next to us, going around Earth, sun with us. Jupiter can carry its moons, Earth can carry its moon, Galileo said. And so it takes the same time. It's with us. It's next to us. 1 year. Same deal. Okay, cool. Let's move on to missions, which I love that topic, and I'll just give you an introduction. You can have some fun with it.